Hi, my name is Shreya Bangara, and since February, I have been conducting research with the MIT Plasma Science and Fusion Center and Commonwealth Fusion Systems under the mentorship of Jessica Chang and Dr. Brandon Sorbonne to develop a reel-to-reel contact critical current measurement system for superconductor tape testing. The development of the novel compact tokamak spark, shown on the lower left, requires the rapid qualification and analysis of high-temperature superconductors in order to construct Rebco-based large-bore high-field magnets. A sample HTS reel is shown on the lower right. Quality analysis involves determining the critical current of an HTS reel, which is the maximum current at which the sample is still superconducting. Traditional measurements involve the manual removal of a section of HTS from a reel, the either soldering of an HTS sample to a wand as shown on the lower right, or clamping on the upper right, and manual insertion into a cryochamber. Reel-to-reel automated spooling systems do exist, such as the Theta Tape Star, that conduct measurements on a subsection of HTS between two rotating reels. However, none of these provide a controllable contact current, which is essential for full quality analysis. I developed 3 designs to automate the clamping of HTS subsamples between reels in order to inject current and measure voltage. All systems can withstand a range of cryochamber temperatures and ambient fields. The first system utilizes a screw linear actuator to clamp a subsection of HTS onto 2 copper current leads. An intermediate testbed of green garolite G10 prevents short circuits, and inserted into the garolite are 2 voltage tabs for measurements. The second system harnesses a pneumatic air cylinder and piston to apply a concentrated, accurate, and non-torsional force to clamp a subsection of HTS to current leads on a similar testbed. The last system does not actively clamp onto the HTS, but rather uses tension to attach the subsample of HTS to 2 quarter cylindrical copper current leads, in which current is injected and voltage tabs in the garolite C10 can record measurements. I conducted simulation analysis using finite element analysis of the screw actuated clamping rig in realistic temperature, field, and force conditions, and the results proved optimistic. The thermal contraction was coordinated and did not introduce any large stresses, and the maximum displacement was at the voltage tab notch attachments, which is remedied by attaching the voltage tabs with bolts as shown here. To determine the voltage tab design, I evaluated press-fitted indium, thin copper springs, and thin copper arches, but decided upon the arches shown in this image for maximum repeatability and recreatability and minimum intrusion. The platform will be made of either garolite G10 for maximum insulation or anodized aluminum for feasibility of manufacturing. The nut material for the 2 clamping rigs will be anodized aluminum in order to prevent conduction to the motors or to the air piston. Along with the mechanical elements of this project, I also continued development of a data acquisition system that harnesses the high power and low cost of a Raspberry Pi to develop and deliver large amounts of currents to HTS samples, while also measuring the voltage drop across the HTS sample. This allows us to create critical current test curves as shown on the lower left to determine the IC, which was created using the testing box on the lower right. In conclusion, although my results are preliminary, they do prove the feasibility of creating this automated reel-to-reel testing system, which, along with the data acquisition box, could revolutionize the testing of HTS and allow for greater efficiency and throughput of quality analysis for fusion devices. My next steps include higher-level prototyping and testing in lab. I'd like to acknowledge Commonwealth Fusion Systems and MIT PSFC for allowing me to work on this project, and the MIT Europe office for funding my research. Thank you.